ఇంటర్మీడియట్ విద్యారంగంలో అగ్రగామి మన NSR ఇంపల్స్ ఎడ్యుకేషన్ ఇన్స్టిట్యూషన్. ఐఐటి జేఈఈ అయినా నీట్ అయినా తిరుగులేని విద్యా సంస్థ NSR ఇంపల్స్.
Very good morning to all. In the last class, we came across the introduction of the D and also F block elements, particularly D block elements. And in this, fundamentals related to D block, or in the introduction of the D block, here there is an important aspect left behind, that is electrode potential. And here, this is also represented as SRPs, standard reduction potentials. Okay. Before going to discuss about the electrode potentials, standard reduction potentials or SRP values, first we should familiar with some important aspects and an important area of the concept. What is that? First one, what is electrode potential? Second one, what is standard electrode potential? And third one, what is standard reduction potentials? How they are calculated? How they are determined? What is the device or what is the apparatus that is used to determine the electrode potentials of the elements, particularly metals, particularly D block elements? That is the first part. Second part, how standard reduction potentials or electrode potentials varies among the D block elements. That is the second part of the concept. What is electrode potential? Actually, this topic is given in the chapter electrochemistry, which is given in the physical chemistry. After completion of the electrochemistry, or if the electrochemistry is completed, then it is very easy to understand the concept of electrode potentials. Then you have no need to think about this. Simply you can read like SRP. Then you can easily understand SRP means standard reduction potential. Then it is convenient to you after completion of the electrochemistry. But here unfortunately, the chapter electrochemistry had to be completed. That will come later on. As a result of that, first I would like to explain what is electrode potential, what is standard electrode potential, and what is standard reduction potential, and what is standard oxidation potential, and what is the difference between these two, how the electrode potentials are calculated, and what about the variation of the electrode potentials among the D block elements is the concept. Right. What is electrode potential? Look at here. Let us consider a beaker. In this beaker, for example, I have taken certain quantity of zinc sulfate. That is nothing but aqueous solution of zinc sulfate. Here, this zinc sulfate is considered as electrolyte. Okay. In this zinc sulfate, here I have kept an electrode. Here this is nothing but zinc rod. Here the zinc rod is suspended in the electrolyte. In this electrolyte, in this aqueous solution, Zn2 plus and SO4 2 minus ions are present. Zn2 plus and SO4 2 minus ions are present. And here in this zinc sulfate, zinc rod is suspended. Right? When a metal rod suspended in the electrolyte with ions of the same metal, automatically there will be a potential difference is created. A potential difference is created which is expressed in terms of electrode potentials. How can you define electrode potential? The potential difference between the metal electrode and its own ions in an electrolytic cell is known as electrode potential. Here this is zinc sulfate electrolyte and this is zinc rod electrode. Here this is zinc rod. When the zinc rod is suspended in the electrolyte, a potential difference is created at the surface of this electrode. A potential is developed at the surface of the metal electrode. How the potential is developed? By appearing by the accumulation of the opposite charges. By the interaction of the opposite charges. How the different charges came into contact? How it is possible? Here. In this zinc rod, zinc atoms are present, metal atoms. The zinc rod loses electrons and forming Zn2 plus ions. Here the electrons are released at this. The electrons are released at this or in this electrode. That electrons appear like this in the electrode. And same time the Zn2 zinc ions are produced. So that zinc ions are released into the electrolyte. Then the condition is like this in the electrolyte. This is the zinc rod with the electrons. Here the electrode is negatively charged. Why electrons are present? How the electrons are entered into the electrode? By the loss of electrons from the zinc atoms, the electrons are released into the electrode. Now the electrode is full of electrons, but the surroundings of the electrons are surrounded by Zn2 plus ions, zinc ions. Zinc ions. Right? Zinc ions. Here, what is the charge of the zinc ions? Positive. What is the charge of electrons? Negative. Here, automatically, there will be an interaction produced or provided or created between the oppositely charged particles or oppositely charged ions. oxidative potential. If the same reaction is reversed, this is the reduction potential. Here this is the reduction and the potential developed is known as reductive potential. How can you define the word electrode potential? The potential developed at the surface of the electrode when the metal rod is suspended in the electrolyte with the ions of the same metal, or when the metal is suspended in the electrolyte with its own ions, is known as electrode potential. I am repeating once again. The potential developed between the surface of the metal electrode not along with the total electrode, only the surface which is getting contact with the electrolyte, that is only involved in the production of electrode potential. The potential developed or the potential difference between the surface of the metal electrode and its own ions in the electrolyte is said to be electrode potential. Here, if the reaction is oxidation, then that is said to be oxidative potential. If the reaction is reduction, then that is said to be reduction potential. In some cases, both oxidation and reduction, both are possible. Such type of electrodes are known as reversible electrode. Reversible electrode means the electrode which undergo both the oxidation and also reduction, means gaining of electrons is take place and also losing of electrons is also take place. Such type of electrode is known as reversible electrode. Okay. Electrode potential is defined. The potential difference between the surface of the metal electrode and its own ions in the half cell or its own ions in the electrolyte is known as electrode potential. Okay, now, right. Here, from this we can move to another one that is known as standard electrode potential. Standard electrode potential. Here this is electrode potential, that is the first part A. This is standard electrode potential, second one. What is the difference between electrode potential and standard electrode potential? And generally, electrode potentials are represented by the letter E. But the standard electrode potentials are represented by the letter E naught. What is the difference between E and E naught of the same metal? What is standard electrode potential? Very simple. If the concentration of the electrolyte is taken as unit activity, what is the meaning of unit activity? 1 molar. If the concentration of the electrolyte is taken as unit activity in this process, then the potential developed is said to be standard electrode potential. Define standard electrode potential. The potential difference or the potential developed between the surface of the metal electrode and its own ions with unit activity in the electrolyte or in the aqueous solution is said to be standard electrode potential. Standard electrode potential. And here there is an important note. How the electrode potentials are calculated, or how the standard electrode potentials are calculated? By using normal hydrogen electrode. And that is also known as standard hydrogen electrode. plus or minus 0.0 volts. Plus or minus 0.0 volts. And here what is the device that is used to calculate the electrode potentials of different metals or different metal ions? And here that is nothing but normal hydrogen electrode or standard hydrogen electrode. This is the reference. This is the reference to calculate, to determine the electrode potentials of the other elements. By using this, the electrode potentials of the all elements in the periodic table are calculated. That may be oxidative potentials or reductive potentials, whatever it may be. For each and every element, the electrode potentials and standard electrode potentials are calculated. But finally, all the oxidative potentials are converted into reductive potentials. Means, according to IUPAC, the electrode potentials of all the elements are expressed in terms of standard reduction potentials. The electrode potentials are standard electrode potentials of all the elements, that may be metal, non-metal, metalloid, whatever it may be. The electrode potentials of the all elements are expressed in terms of reduction potentials. Means standard electrode potentials, if the word standard electrode potential is used at anywhere in the electrochemistry or any part of the chemistry, means that is nothing but standard reduction potential. Okay. But what about the condition that is oxidative potential? During the numericals or at anywhere, if the reaction is oxidation and we are wantedly expressing the electrode potentials as a standard oxidation potential, then only you have to think about the oxidation. Otherwise, standard electrode potential means that is nothing but standard reduction potential. That is according to IUPAC. For a given element, both the standard reduction potential and also standard oxidative potential values are same. But they have opposite signs. Here these are having same value. Magnitude is same, but with the opposite signs. Let us consider with an example for the same thing. Example zinc. Here Zn2 plus Zn means what? Zn2 plus 2 moles of electrons gives rise Zn. This is the notation. Its value is equal to minus 0.76 volts. This is the standard electrode potential E naught. Standard electrode potential means this is nothing but standard reduction potential. Okay. But what about the oxidative potential? Oxidative potential is equal to 0.76 volts. Then how can you represent the oxidative potential? Zn by Zn2 plus. Here reduction potential and oxidation potentials are having same magnitude, but the difference is only the sign convention. Okay. And now this is about the electrode potential, standard electrode potential, and also expression or representation of the electrode potentials. That may be reduction potential or oxidation potential. For a given metal or given element, here both the reduction potential and oxidative potentials are having same magnitude, but the signs are different. Right. And here, to calculate the electrode potentials, is dilute HCl or aqueous HCl with 1 molar concentration. H2 gas 1 atmosphere. This is the construction of standard hydrogen electrode which has the electrode potential as 0.00 volts. And here this is the reversible reaction. Means what? H2 gives rise to H plus 2 volts of electrons. This is known as oxidative potential. 2H plus 2 volts of electrons gives rise H2. This is known as reduction potential. But here this is the reversible cell. Then how can you represent 2H plus and H2 gas 1 atmosphere and 1 mole. Here this is reversible cell. So we have to represent the electrode potential of this normal hydrogen electrode or standard hydrogen electrode as plus or minus 0.00 volts. And here this is oxidative potential. Here it is expressed with plus. This is reduction potential with minus. Now, when the concentration of HCl is 1 molar and the hydrogen gas supplied with 1 atmosphere, then there is an equilibrium established like this. Then this is said to be reversible cell. Okay. Now this normal hydrogen electrode with 0 volts of electrode potential is connected with another half cell. This is half cell. Okay. Now, suppose in this half cell the reaction is carried out like this. Zn 2 plus 2 volts of electrons gives rise Zn. Here, gaining of electrons is take place. Okay, gaining of electrons is take place. Then, what about the reaction that takes place at this electrode? Here, electrons He2 gives rise to H plus 2 volts of electrons. Here, this is the reduction. But here, these electrons are given by normal hydrogen electrode. Here loss of electrons is known as oxidation. So this is oxidative potential. When oxidation is take place at the normal hydrogen electrode, automatically here the reaction is reduction. If this is oxidation potential, automatically it becomes reduction potential. If the reduction is take place at this normal hydrogen electrode, then here oxidation is take place. Then what about the reaction? What about the reaction? Zn gives rise Zn 2 plus 2 volts of electrons. Then what about the reaction? Take place here 2H plus 2 volts of electrons gives rise H2. This is 1 atmosphere. This is 1 molar. And here this is 1 molar concentrated. Such type of electrodes are known as reversible electrodes. Such type of electrodes are known as reversible electrodes. And based on this concept, here we are adding the galvanometer, which shows the reading correct. Okay. And here, by using the normal hydrogen electrode, we can calculate the reduction potentials or oxidative potentials for each and every element in the periodic table. Each and every element in the periodic table. Okay. But what about the theoretical explanation? This is practical experiment. By taking reading from this, we can directly put the value for this. Here, zinc metal. Here this is oxidation, this is reduction potential. E naught is equal to minus 0.76 volts. From this we can take the value. That is known as reduction potential. For the same thing, oxidative potential is E naught is equal to standard oxidative potential is equal to plus 0.76 volts. Okay. And take for another example, let us consider copper. Cu2 plus by Cu means what? Cu2 plus 2 moles of electron gives rise Cu. And E naught is equal to plus 0.33 volts. And what about the oscillator potential? Cu by Cu2 plus means Cu gives rise Cu2 plus 2 moles of electrons. E naught is equal to minus 0.33 volts. Each and every element has both oscillator and reduction potentials, but they have same magnitude. But the difference is only the sign convention. Sign convention. If the oscillation is take place at the normal hydrogen electrode, then at another electrode reduction is take place. This is one half cell, this is another half cell. Then the circuit is completed. And next one, if the reduction is carried out at the normal hydrogen electrode, then oscillation is take place at the another half cell. Right? This is about the calculation or determination of the electrode potentials and also standard electrode potentials. And what about the formula, or what about the expression that is used to calculate the electrode potentials? Here in textbooks, the electrode potentials are given in terms of reduction potentials. They are represented as standard reduction potentials. Okay? But here there is another expression used to calculate the electrode potentials. That is nothing but Nernst equation. What is Nernst equation? The mathematical expression which is used to calculate the electrode potentials. The mathematical expression which is used to calculate the electrode potentials based on the concentration of the ions in the electrolyte is known as the Nernst equation. Okay. Here what about the Nernst equation? During the calculation of the electrode potentials, here we can take them as metal electrode and non-metal electrode. Non-metal electrode. Okay. Metal electrode, let us M losses electrons, Mn plus N moles of electrons. N moles of electrons. This is reactant and this is product. According to the Nernst equation, electrode potential E is equal to E naught minus RT by NF. Ln concentration of the product by concentration of reactant. Here, this is the expression. Now we have to substitute the concentrations or values of the given species in the equation. This is the concept. From this, we can write E naught minus by taking or by converting this log E value into logarithmic values. Logarithmic values here 2.303 into RT by NF into log concentration of product by concentration of reactant. Here R is equal to gas constant, T is equal to standard temperature, F is equal to Faraday. These are all the constant values. From that we can write E naught minus 0.059 by N into log concentration of the product by reactant. same expression is represented as E is equal to E naught minus 0.059 by N into log concentration of M power N concentration by M concentration. Concentration. By substituting and here I am representing the oxidative potential. For the same thing we can write the reduction potential also. How? That is M plus M moles of electrons gives rise M. Here this is solid, this is aqueous solution. Okay, aqueous solution. This is the reactant and this is product. And by substituting these values in this expression, E naught minus 0.059 by N into log concentration of product. Here products are changed. Product means M by M power N plus. You have to follow the textbook, the UPSC convention. And here this is product M. This is the reactant M power N plus. This is an aqueous solution, this is solid state. Solid state, the concentration of metal is equal to 1 unit activity 1 by Mn plus concentration. From the same thing we can write E is equal to E naught plus 0.059 by N into log concentration of Mn plus. Here this is the concentration of ions. By take them into numerator, we can get the next equation like this. This is the calculation of the electrode potentials in case of the metal electrodes. In case of metal electrodes, when the reduction is take place. Now this is reduction potential. Take for example, let us consider zinc. Then what about the standard electrode potential? Minus 0.076 volts. Okay, but in case of the non-metal electrode, the same thing is A plus N moles of electrons gives rise Am minus. This is solid and this is the aqueous solution. Apply the same thing here. E is equal to E naught minus 0.059 by N into log concentration of product A power N minus concentration by A concentration. Here this is solid. Its value is taken as 1. 0.059 by N into log concentration of A power N minus. This is for non-metal electrodes. This is for non-metal electrode. This is the calculation of the electrode potentials. Calculation of electrode potential. This is nothing but the standard reduction potential. And this is reduction potential or electrode potential. Reduction potential or electrode potential. This is about the condition. This is about the next equation applicable for both metal electrode and also non-metal electrodes. Right. And here, in the same way, by using the next equation, we are calculating the electrode potentials. We are calculating the electrode potentials of all the metals in the D block elements. And same time, the elements in the periodic table are arranged in a systematic order, which is represented as electrochemical series. Electrochemical series. Here the metal that is present at the top another one. Fe2 plus by Fe means what? Fe2 plus 2 moles of electrons gives rise Fe. That is minus 0.44 volts. In between these two, we can write another one also. What is that? Zn2 plus by Zn. Zn2 plus by 2 moles of electron gives rise Zn. That is minus 0.76 volts. After that, we can write another one. That is H plus 2H plus by H2 gas means 2H plus 2 moles of electrons gives rise H2. That is plus or minus 0.00 volts. These are all the electrode potentials. Which electrode potentials? Standard reduction potentials calculated by using Nernst equation. And after this, we can write Cu2 plus YCO. This is also a reduction. Cu2 plus 2 moles of electrons gives rise Cu. That is plus 0.33 volts. And next one, Ag plus by Ag. Ag plus 1 mole of electron gives rise Ag. This is plus 0.8 volts. And finally, the element with the highest SRP value is fluorine. F2 by 2F minus. F2 plus 2 moles of electrons gives rise 2F minus. That is plus 2.53 volts. This is the lowest value minus 3.3 volts. This is the highest value plus 2.53 volts. Means what? In electrochemical series, as we move from top to bottom, here the SRP value gradually increases. How can you say gradually increases? The negative value gradually decreases up to hydrogen electrode and then increases up to 2.53 volts. This is about the electrochemical series. Okay. But here, based on the values given in the electrochemical series are, if you are properly understanding the construction of the electrochemical series, then you can easily understand the nature of the element, the reactivity of the element, the behavior of the element also. How? Take for example. In electrochemical series, as we move from top to bottom, the SRP value gradually increases. Means what? The negative value gradually decreases and positive value increases. Okay. Here, let us consider a generalization. The metals with the lowest SRP acts as strongest reducing agent. The metal with the lowest SRP value acts as strongest reducing agent. Okay. And in the same way, the element with the highest SRP acts as strongest oxidizing agent. With the lowest SRP, reducing agent, strongest reducing agent. With the highest SRP, strongest oxidizing agent. Means what? As the SRP value increases, as the SRP value increases, the reducing power decreases and oxidizing power increases. elements, that may be metal or non-metal, properly by using the electrochemical series. What is electrochemical series? A series in which the electrode potentials are systematically arranged. A series in which the electrode potentials are systematically arranged is known as electrochemical series. Here these are all the reduction potentials. According to UPSC, electrode potential means reduction potential. Here these are all the reduction potentials. This is the explanation. These are the values. Okay. What is the significance of the electrochemical series? Based on the electrochemical series, or by understanding the construct of the electrochemical series, we can understand, we can evaluate the reactivity, the behavior, the attitude of the elements that may be metal or non-metal in the periodic table. Okay. But how can you calculate the electrode potentials? By using normal hydrogen electrode, which has the electrode potential as 0.00 volts. And by using, these are all the values that are calculated by taking the electrolyte value as unit activity, 1 molar. 1 molar unit activity. And next one. And here, next one, what is the expression that is used to calculate the electrode potentials? Not standard electrode potential. Standard electrode potential means concentration of the electrolyte should be 1 molar. Electrode potential means that may be anything. 0.1 molar, 0.2 molar, 0.5 molar, 0.75 molar, 1.2 molar, 3 molar, whatever it may be, that is electrode potential. If you are representing or if you are using the word standard, then you should confine to 1 molar. If you are using the word electrode potential or reduction potential, then the concentration of the electrolyte should be represented in a small bracket beside the formula of the electrolyte. Then the formula used to calculate the electrode potentials are E is equal to E naught plus 0.059 by M into log concentration of ions. Log concentration of ions. Mn plus M power n plus concentration. This is for the metal. This is for the metal. In case of non-metal, here E is equal to E naught minus 0.059 by N into log concentration of A power N minus. Here what are the examples for this metal? That may be zinc, that may be copper, that may be silver, that may be iron, that may be manganese, whatever it may be, that is the condition. Here you should consider them as the reduction only. Here this is non-metals, means chlorine, fluorine, oxygen, okay, oxygen, bromine, iodine, etc. These are all the non-metals. For the non-metal electrodes, you have to use this one. That is also reduction potentials only. You have to consider only the reduction potentials. Here the formula used is known as Nernst equation. By using Nernst equation, we are calculating the standard electrode potentials and we are calculating the electrode potentials. From that we can construct the electrochemical series. From that we can understand the nature of the elements or the behavior of the elements properly.
ఇంటర్మీడియట్ విద్యా రంగంలో అగ్రగామి మన ఎన్ఎస్ఆర్ ఇంపల్స్ ఎడ్యుకేషన్ ఇన్స్టిట్యూషన్. ఐఐటి జేఈఈ అయినా నీట్ అయినా తిరుగులేని విద్యా సంస్థ ఎన్ఎస్ఆర్ ఇంపల్స్.